This video will describe the simple process of creating a bracket model by setting up a static analysis and performing a parametric study for analyzing a varying load. After an initial analysis with the load applied to the bracket holes along the negative y-axis, the sweep will start at 0 degrees and rotate 45 degrees up to 180 degrees. 3D is the default space dimension, and for this example, under Structural Mechanics, add Solid Mechanics to the model by right-clicking or clicking the Add button below the table. Select a stationary analysis and click Finish. The first order of business is creating the parameters that we will be using later. Theta 0 will be used to indicate the direction of the load. P0 is the peak load intensity applied to the bracket holes. Y0 and Z0 are the coordinates of the center of the bracket holes. The geometry is ready to be imported. Right-click the Geometry node and add an import. Click Browse, and in your Comsol folder under Models, select the bracket.mphbin tutorial model, click Import, and the geometry will appear in your graphics window. We need to create two selections boxes under the Definitions node that we will reference later on. The first box selection will contain the bolt domains on the bracket. Once the necessary values are entered, include only the entities inside the box to eliminate the main bracket geometry. Click on the wireframe button to view all the bolts, making sure they are all highlighted. Create another box. And this time, we want to include boundaries instead of domains. These are the load-bearing boundaries of the holes. Re-click the wireframe button to view the hole geometry once again. Right-click Definitions and select Variables. Enter in the values shown with the names and expressions. The angle variable is used to help define the load intensity. The load intensity defines the pressure distribution file, which we will come back to later on. This last part is added to ensure that the load is only applied to one half of the hole. Create a rotated coordinate system, which defines the orientation of the load applied to the bracket holes by adding theta 0 as the beta value. The material setup here is easy, since we want the hole geometry to be structural steel. Now add a fixed constraint by right-clicking the Solid Mechanics node and selecting More, Fixed Constraint. We are adding box 1 as the selection to specify that the bolts will remain in the same position. A boundary load is added by right-clicking Solid Mechanics and selecting the boundary load option. Choose the box 2 selection. Under Coordinate System, select Rotated System 2 and type Load Intensity into the second row of the Load table. To run the model, right-click the Study node and select Compute. You can see the von Mises stress distribution with an exaggerated picture of the deformation occurring mostly in the bracket arms. Add a volume integration to see the reaction forces in the X, Y, and Z component forces. Right-click Derive Values and add a volume integration. In the Selections list, select box 1. In the Expression tab, click the Replace Expression button and go to Solid Mechanics, Reactions, Reaction Force, and select the X component. Click Evaluate. Do this for the Y and Z components as well. You can also manually enter the expression, in this case by changing the component letter. The evaluated results match our expectations, with the entire load in the Y direction, and zero load in the X and Z directions, except for negligible numerical errors. Adding a parametric sweep to the model will allow us to view the model with different load angles. Go into the Stationary Study node, and under Study Extensions, check the Continuation box. Click the Add button, and then click the Range button to define the range. For this sweep, we will start at 0 degrees and rotate the load 45 degrees until we reach 180 degrees. Right-click Study 1 to recompute the model. Now we can view the 5 different solutions, dependent on the angle of the load. Add another volume integration to view the reaction forces at the different parameter values. This force is always 0 in the x direction, whereas the y and z directions share the load, depending on the angle. Creating a graph plot gives a better view of the parameterized results.